Excuse me, Professor. I think you're on mute.
Hi, sorry before you for listening to the lecture online. Sorry, I forgot that I was on mute. Thank you for letting me know. All right, so yeah, I was explaining, so one more time, we want to prove that if you have a hypothesis A1 is equivalent to A2 and AN is equivalent to AN plus 1 and so on, then you can conclude A1 is equivalent to AN plus 1. And the basis step, when you have only one hypothesis, is trivial. Now, the inductive step would be that you take the assumption that the statement is true when you have n hypothesis. That means A1 is equivalent to A2, A2 is equivalent to A3, and AN minus 1 is equivalent to AN. So let's actually, sorry, this is n minus 1 many hypothesis. Then the first one is equivalent to last one. So this is your induction hypothesis. And now you want to show that the same is true when you have n hypotheses. Now you add one extra hypothesis here, right? You add one hypothesis. The hypothesis is AN is equivalent to AN plus 1. And now you want to prove that A1 is equivalent to AN plus 1. Now, how do you do that? Well, here, again, the idea is to apply the transitivity and also the transitivity of the proof symbol. So if you call this set here, if I call this set here gamma, then gamma is the set of hypotheses, and I know it implies A1 is equivalent to AN. Now, gamma, we added to gamma one more formula that says AN is equivalent to AN plus 1. And now what do we want to show? We want to show that this implies or proves that A1 is equivalent to AN plus 1. But note that this alone, these together with only one of the hypotheses, sorry, not hypothesis, the conclusion here of the inductive hypothesis. So gamma proves, let me write this down. So what we know that gamma proves A1 is equivalent to AN. And we know A1 is equivalent to AN, and the formula AN is equivalent to AN plus 1. Together, these two formulas, let me put them in a set, they prove A1 is equivalent to AN plus 1. This is the transitivity of by implication. Now gamma proves both of these formulas. Gamma proves this is the inductive hypothesis. Nope, sorry, this is in gamma. So this belongs to gamma. Therefore, gamma proves it. This one so what did I say? This is the new hypothesis, right? It's a new hypothesis. But gamma doesn't prove this, but we are not writing a gamma proof. We wanted to show that gamma union A1 equivalent, sorry, AN equivalent to AN plus 1 proves here. This is what we want to prove. Proves AN is equivalent to AN plus 1. Sorry, my bad. We wanted to prove this A1 is equivalent, but not the transitivity of the group, because a gamma union, this formula implies both of these formulas, this one and this one, and these two together they prove A1 is equivalent to AN plus 1. Therefore, by the transitivity of the proof, since gamma proves both of these, gamma proves this. All right, yeah, this is an easy induction argument. Now, what is the equational style proof? How do we write it? Again, we want to be syntactically correct and always annotate all of our steps. So that is not changed. Our axioms are the same. Rules of inference are the same. They don't change. Only the style of writing is changed. That means in the Hilbert style, we were writing steps of formulas like this, and here we annotated them. Now here, we're going to do things a little bit differently. This time we are going to write formulas that each formula in the previous step is equivalent to the formula that comes in the next step, and so on. If there's A3 here, A2 is equivalent to A3. So our idea is to, instead of writing A1 is equivalent to A2, A2 is equivalent to A3, and all the way to AN minus 1 is equivalent to AN, this whole fact can be written in the following way. Start with A1, and we know it's equivalent to A2. So here's really the equivalence. But in this style, just to be perhaps a little bit more clear, instead of this equivalence or by implication symbol, we are using this double-sided arrow, which technically is the same thing. It says the same thing in mathematics, right? We use this double-sided arrow to say if and only if, and by implication has exactly the same meaning. So this is really the fact that A1 is equivalent to A2, and A2 is equivalent to A3, and so on. And here, right in front of the arrow, or on top of the arrow, just write the annotation, why A1 is equivalent to A2. You explain it here. Why A2 is equivalent to A3. Explain it here. And note that I'm not assuming that these are necessarily given hypotheses. Otherwise, we just write hypothesis, and there's nothing to, you haven't achieved anything. But sometimes you prove equivalences using what you already proved, or write an axiom, or just get it from a rule of inference like Leibniz or equanimity, and so on. And then we finally write AN minus 1 is equivalent to AN, and we annotate Y. And note that, but by what the previous theorem says is, now we can conclude A1 is equivalent to AN. So once these steps are complete, then your conclusion would be that A1 is equivalent to AN is a theorem. Now, it could be an absolute theorem if you didn't do it, if you didn't use any hypothesis, but if you use hypothesis from set of gamma, then this would be a gamma theorem. right? So first we're going to prove some trivial facts about formulas using this method, and then we'll use more, even learn how to use hypothesis exactly here, because it's not going to be completely obvious in the beginning how to use hypothesis in this style, but we'll get to that. First of all, show that this is an absolute theorem. And first thing that you notice that we have seen this before, it's one of your axioms, but it's just the order is changed. In fact, we had this axiom called the introduction of negation that tells you that negation of A is equivalent to A is equivalent to bottom. And the only thing that has changed is that, yeah, perhaps you take A minus 1 to the other side of this equivalence. And that also gives you the idea how to prove this. In a Hilbert style, it's going to take you like 3 or 4 steps to use equanimity and symmetry and so on. But it's a lot easier when you write an equational style proof for this. Start with the formula that you want to prove. And again, by associativity, we said that we can put the brackets anywhere we want when we have sequences of these equivalences, consecutive equivalences. Doesn't matter which operation you do first. By associativity, they're all the same. And now, what you want to do is use symmetry, change the places of these two. Sorry, that's probably not going to give me the formula. Let me see. What did I want to change? I wanted to take these two, right? Now use the symmetry, and you get this. And here I annotate. You can write just axiom, but I'll explain. The axiom is called the symmetry of equivalence. Now in the next one, I didn't even write the brackets, right? The brackets are here, but it doesn't matter where they are. All those formulas are equivalent, right? So this is, as you can see, it was a lot easier, but why am I done here? The reason that we are done and the proof is complete, we have just shown that the formula that we wanted to prove, namely this one, is equivalent to an axiom. Therefore, it must be true, right? This was a consequence of redundant true that if you have a formula, we showed that all axioms, in fact, all the absolute theorems that we prove, they are always equivalent to true. Sorry, said to top, which we always consider as the statement as a tautology, right? And now if I show that, and I have another formula, B is also equivalent to A, then again, by using the transitivity of implication, or sorry, by implication, I can conclude that B is equivalent to top, which by redundant true is same as proving B. Right? So here, if this is my B and this is my A, I showed that B is equivalent to A, and I already know that A is an absolute theorem because it's an axiom. Therefore, B is an absolute theorem. Any questions? So this is a style of proof that is very flexible, but usually it makes things easier, especially when you want to show equivalences of formulas, or what essentially that's going to be tautological equivalences when we give meanings to these. So let's move on to another theorem. Negation of A is equivalent to B is equivalent to negation of A equivalent to B. Now, in order to prove this, there are, again, different ways of doing this. Let me see what's going to be the easiest way to do this. I could, for example, start from this formula and write a series of equivalences and end up with this formula, right? Or I could start with this formula and write a series of equivalences and at the end finish with B. So there are a lot of choices. Or you could start with the whole formula and show that this is equivalent to something that we've already proved, or we know it's an absolute theorem, could be an axiom, right? So there are many different choices. You could even start with this first and then end up with negation of A is equivalent to B. Let me see. I think I'm going to start with this. That's just the first thing that comes to mind. Negation of A is equivalent to B. And I want to use the axiom of introduction of bottom, or the thing that we proved here. I don't think we need that. That's the same. By the way, we are going to call this also axiom of introduction. Is this the same thing, right? Your order change. There's no reason not to call it an axiom. All right. And I know this is equivalent to A is equivalent to B, equivalent to bottom, right? I applied it to this formula. You know that negation of any formula is it's equivalent to the formula is equivalent to bottom. That's one of our axioms. Now, again, by associativity, I'm not going to put the brackets anywhere here because the next thing that I want to consider is, in fact, B is equivalent to A, and I want to replace that with what? With negation of B, right? I know it's equivalent to negation of B. Any formula equivalent to bottom is equivalent to the negation of the formula. Now, how do we do that exactly? Note that if I didn't have this here, I can just say axiom of introduction of bottom, and we're done. But since we have this extra formula, it's not a formula, but extra bunch of symbols, and this here, B is equivalent to bottom, is only a sub-formula. it doesn't mean I cannot do it, but I need to be more careful with my annotation. So I know I can get negation of bottom here because B is equivalent to bottom is equivalent to negation of bottom. But what we actually did here was an instance of Leibniz. In fact, in the annotation, you should write Leibniz, which I'm denoting it by this, where we applied it to the axiom that we know. Again, here you write the just a template of the axiom, right? It doesn't have to be P, or you just write axiom of introduction of bottom again. But what is the C part of the Leibniz here? The C part, note that Leibniz told me that if I know two formulas are equivalent, then if I pick any variable P and any formula C, if I replace that P with those two formulas, the resulting formulas are going to be equivalent. Now, where did I apply this exactly? I knew that negation of B is equivalent to B equivalent to bottom, right? We know this, or if you wanted to write it here, the same thing. Now we call these both axioms of axiom of introduction of bottom. Now, I know for any formula C, if I substitute P with B equivalent to bottom, it's equivalent to when in C, I substitute P. I'm going to leave a little bit more space here. C, I substitute P with negation of B. Right? This is Leibniz, an instance of Leibniz. Now, here exactly what is my C? Leibniz tells me I can do it for any C. Now I'm applying it for a specific C. What is the C of the formula exactly? It's equivalent to what? A is equivalent to A? Now, it's not A is equivalent to C. You're replacing P. You want P somewhere there. A is exactly, A is equivalent to P, right? If your C is A is equivalent to P, now look at the substitution. This one, in the formula A is equivalent to P, substitute P with E equivalent to bottom. So what do I get? A is equivalent to B equivalent to bottom. And what do I get here? In the formula A is equivalent to P, just replace P with negation of bottom. What do I get? So, and this is exactly what I want. That's how I'm able to write the negation. A is equivalent to negation of B. And this is exactly what you should do every time. Note that again, if I did not have this, you don't need Leibniz. It's just they're equivalent. It's the axiom. But if you want to just replace a part of the formula, a sub-formula of your entire formula, it's something that you know it's equivalent to it, then you need to use Leibniz officially. And it might sound difficult and a lot of hassle to do it, but it's actually very, very easy to find out what the C of the formula is. The part that you want to substitute, call it P. And that's the C part of your formula. You just have to write the C part is A is equivalent to P. Now, you also need to say that P is a fresh variable. P is fresh. What does it mean, fresh? Let me remind you. Fresh means it doesn't occur in any of the formulas that are there. In this case, A and B. P is a fresh variable, means it does not occur in A or B. Because if it did occur in A or B, then the result of this, if there's P in A, then substitution would change A to something else, right? You don't want that to happen. So if P was in A, you cannot apply this. I mean, you can apply it, but you don't get A anymore here. You get something else. So in order to keep A, you want P to be fresh. It also doesn't occur in B, so that there's no fishy business here. Here, it's not actually important that it doesn't occur in B, but in general, always say it's fresh. I know it's a kind of a long annotation for something as trivial as this, but it is actually quite helpful for the reader to understand what happened here. Maybe in this case, was obvious, but not all the equivalences are that obvious. And which part of the formula you replace with what? But once you get used to this annotation and how to read it, then it's quite helpful. And it helps the reader, or if you write a proof, next time you look at it, you'll understand what you did in a step. Anyways,
Professor,
yes.
what if we just said on the C part, what if we just said only P? Why we need to say A is equivalent to P?
But C part is P, what do you get?
And then we replace instead of B,
This is what
instead
you
of
get.
P.
I mean, this is, this is what you get is just the axiom that you already have. And why did you use Leibniz to get the axiom that you already have? When you use it for P, when C part is P, is actually what you get is the numerator, nothing new. So the rule of the Leibniz rule doesn't give you anything new.
Oh, okay. Thank you.
Yep. Okay, I just realized that I actually didn't want this. Even though, okay, it was a good practice, but I wanted to apply the same thing for, so I will erase this. Sorry about that, because I wanted to get negation of A, not negation of B here. So let's step back a little. How do I get negation of A? Let's just apply symmetry first. So we're going to use the same thing. I know B is equivalent to bottom is equivalent to A. So let's just first apply the symmetry. Right? Now, in order to apply the symmetry, again, the same thing. I wanted to replace this with something equivalent to it, which is bottom is equivalent to B. So we are using Leibniz. For what? For an axiom. What was the C part of the formula? This is the one that I want to replace. Call it P. The C part is A is equivalent to P. And I say P is fresh. And that's complete. Now that we have done this, we know that the brackets do not matter here. I can take this. A is equivalent to bottom is equivalent to negation of A. So I can replace this with negation of A. I get negation of A is equivalent to B. And here, what did we do? We replaced this with negation of A. So there's this extra, this is a sub formula of the entire formula. That's why we need to use Leibniz. You call this P for the C part. So we are using Leibniz again for an axiom. What was the C part this time? This time is P is equivalent to B. P is again fresh. Now we are done. Why are we done? This first formula is equivalent to the last one. And that's what we wanted to prove. We didn't use any hypothesis along the way. Therefore, this must be an absolute theorem. We only used axioms. Any questions? So here, let me write back what it was. Okay, I think this was clear, so I'm going to erase this. Yes. For the assignment, if you can use this style, yes. If it helps you, yes, you can. Now, the next corollary of this is the same theorem, but instead of negation of A here is negation of B. So negation of A is equivalent to B is also equivalent to A is equivalent to negation of B. And by the way, in order to understand these two formulas, note that what does this say? It says that basically it's not the case that A is equivalent to B. So that means A is not equivalent to B. But A is not equivalent to B is same as saying that A is not equivalent to, sorry, A is equivalent to negation of B. Right? If A is not equivalent to B, then A is equivalent to negation of B. And note that any formula is equivalent if it's basically a consequence of redundant true, right? Because any theorem is equivalent, or anything that is true is equivalent to the tautology. So anything that is false is equivalent to the contradiction. The proof of this is the same. Start with negation of A is equivalent to B. Here, just use the axiom of introduction of bottom. This is exactly what I wanted to do last time. Now you can take this part, A is equivalent to bottom, and I want to replace it with the negation of bottom. Since this is a sub-formula of the formula itself, I'm going to call this P, and I take the C part to be A is equivalent to P, and just write what axiom I used. Or here is the axiom that we used, right? B is equivalent, bottom is equivalent to negation of B. And the C part is this, P is fresh, and then it allows you to replace this P with negation of B. So this is similar. There's a rule of thumb. As you notice that I told you that we have different options where to start. Could have taken this part of the formula and show that it's equivalent to negation of bottom. There are a lot of different ways of proving a theorem. In the equational style, as a rule of thumb, it's easier sometimes to start with the more complicated side of the equivalence, if you wanted to show the equivalence, like this one, double negation. Let's prove that the negation of A is equivalent to A, something that we all know is true. But how do we prove it in our proof system using axioms and rules of inference? So when I said as a rule of thumb, start with the more complicated side of the equivalence, this negation of A sounds more complicated than A. So let's start from there. Negation of A. Now I want to write a series of equivalences and end up with A. So when negation is involved, that means perhaps it's a good idea to start with the axiom of introduction of negation. So I'm going to think of this. Let me write this a little bit larger. So take this here. Negation of A is the negation of A, right? This is what it actually is. It's the negation of A. And if negation of A, you call it B, then you know negation of B is same as is equivalent to B is equivalent to bottom. And that's an axiom. You don't need Leibniz here. You're just applying the axiom of introduction of negation. Sorry, did I say introduction of bottom before? It's introduction of negation. Sorry about this. The names are, the axioms will be given to you. So and that's it. This is the formula B is equivalent to bottom. Now apply the same thing for this negation. I want to replace this negation of A with A is equivalent to bottom. But again, this negation of A is not the entire formula. It's a sub-formula of this whole formula. So in order to do that, I need to apply Leibniz. And I'm going to take this, call it P. Now the C part of the Leibniz is P is equivalent to bottom, right? So you can easily do this. You just say Leibniz, the same axiom. What was the C part? C part, I call this P. So P is equivalent to bottom. C part is P is equivalent to bottom. Again, P is fresh. P is always fresh in Leibniz. We'll just say it. Now what do I get? Here I get A is equivalent to bottom is equivalent to bottom. Again, I have the brackets here, but it doesn't matter where the brackets are, right? Because of associativity. We say we don't write always this step, another step for associativity. We'll just skip that part. We don't want to write too many equivalences. So now what? That means I can put the brackets wherever I want. I want to put it here. Now bottom is equivalent to bottom is equivalent to top. That's an axiom of top versus bottom. So I can replace this with top. And get A is equivalent to top. But I need Leibniz because this is not the entire formula, it's a part of the formula. So let's call this P. Now I know is if I use Leibniz again, top versus bottom, let me write axiom of top versus bottom, the C part of the Leibniz, A is equivalent to, quotation, A is equivalent to P, where P is fresh. Now that allows me to replace this part with top. Now, what did I want? I wanted A, but A is equivalent to A is equivalent to top, right? That's the redundant true. Let me again write what the redundant true was. It was a theorem, absolute theorem that we proved A is equivalent to A is equivalent to top, right? So A is equivalent to top is equivalent to A. We've already proved this. I don't need Leibniz here. Why? Because I'm just replacing the entire formula with what it's equivalent to, and that is A. So redundant true. Now the first formula is equivalent to the last one. So negation of A is equivalent to A. Any questions? Now the next theorem. You see, we are proving a lot of trivial facts. Why are we doing that? Because by the transitivity of proof, I mentioned last time that any theorem that you prove, you can apply it to the next proof. Now, for example, I know now that we have proved negation of bottom is equivalent to A, now we are allowed to use it because we know it's true. So we extend our toolbox with these trivial things that could have been axioms, but they're not, because we didn't pick them to be axioms. In some other proof system, they might pick negation of A to be equivalent to A as an axiom, but we did not. And you want to keep the list of axioms as simple as possible, right? And then you can prove more stuff. And then use them again. Now here, start with, here it's actually, we didn't start with the more complicated side, but we could have, right? We could have started with the negation of bottom and go from below to top. It's exactly the same symmetric proof. So it doesn't matter which part you start with. Start with top. I know top is equivalent to bottom is equivalent to bottom. That's the axiom. And bottom is equivalent to bottom. Another axiom tells me that it's equivalent to negation of bottom. Which axiom? Axiom of introduction of negation. Why? Because the axiom of introduction of negation tells me that negation of any formula A is equivalent to A is equivalent to bottom for any formula A. The axioms are schematas, right? They do not apply to a specific A. Apply it for bottom. So bottom is equivalent to negation of bottom. I have bottom is equivalent to bottom. It's the entire formula I want to replace with negation of bottom. So I don't need Leibniz. Just again, this means equivalence, right? Just think of these double-sided arrows as equivalence. You just write your formula, bottom is equivalent to bottom is equivalent to negation of bottom. So now we know that top is equivalent to negation of bottom. Another, the mirror image of that is that the bottom is also negation of top. The proof is, now we actually, in the proof, I'm going to use what we already proved. This one. Because I proved this, I know I can use it. So how do I start? Let's start with this negation of top. Now I know that top is equivalent to negation of bottom. So I pick this sub formula, just the top itself. That means do not take negation. Now if I call it P and use Leibniz for the theorem that we just proved, that top is equivalent to negation of bottom, where the C part is negation of P, and obviously P is fresh, but P doesn't have to be fresh here because any P is fresh, right? The reason that I didn't write P is fresh here, I mean, if you write, it's okay, but it's not necessary to write P is fresh because there is no A or B. There's no formulas. Any P is fresh. There are no variables here. So it would be just redundant to say P is fresh. But the C part, if I take it to be, again, negation of P, then it allows you to replace or substitute top with what is equivalent to it. And I know it's equivalent to negation of bottom. So we get negation of bottom. Now apply the double negation. Negation of any formula, we just proved that it's equivalent to the formula itself. So that means negation of bottom is equivalent to, so negation of top is equivalent to bottom. Another pretty much obvious theorem that for any formula A or top is an absolute theorem. Note that again, when it comes to semantics, any absolute theorem must be a tautology. And that's something that we prove later on. So far, we are talking about only the syntax. But later on, we are going to show that our syntax coincides with our semantics. That is, whatever is an absolute theorem is in fact a tautology, right? So just to guide you through what exactly these formulas are, you know that such a formula is always a tautology because no matter what A is, a formula or top is always going to be true, right? Therefore, this must be an absolute theorem because it is a tautology. But how do you prove this? Using what we have so far. And what we have so far is not much, but it's getting more and more. So let me see. Actually, I need to think about this. I can, now you better, when you start seeing like this, before writing things down, have a little bit of strategy in your head, what you want to achieve here. For example, if I take this top, if I replace it with for example, if I replace it with negation of bottom, it's not going to help me, right? So where am I going with that? But if I replace it with bottom is equivalent to bottom, which I know top is equivalent to bottom is equivalent to bottom. That's the axiom of top versus bottom. Then I'm going to end up with an equivalent formula, this. But then I know if I can use the associativity, if I use the associativity, sorry, not the associativity, the distributivity, I'm going to get A or bottom is equivalent to A or bottom. But this part, I know it's true. It's an absolute theorem. Because any formula is equivalent to itself is an absolute theorem. So that's our strategy. Now you just have to write down things properly. So let's start with the whole thing with the formula A or top. There's no other way here because we're not proving an equivalence, even though we are using equational style. But by showing this is equivalent to something that we know is an absolute theorem, we are done. So if I call this P, because again, I just want to substitute just part of the formula, so I need to apply Leibniz. Leibniz. I want to apply it to top is equivalent to bottom is equivalent to bottom. Now the C part is what? Exactly A or P. Now P is fresh because it shouldn't occur in A. Otherwise, we're not going to get A or bottom equivalent to bottom. Now, as I mentioned, just use the associativity. Sorry, again, I said associativity, just distributivity. And then I'm applying it to the entire formula. So no Leibniz is applied here. Distributivity of or over equivalence, which was an axiom. It was one of the axioms. Let me write here, just to remind you that this is an axiom. Now, what do we get? A or bottom is equivalent to A or bottom. Now, the last formula is an axiom. Note that we proved, not an axiom, sorry. It's a theorem. It's an absolute theorem. It's called the reflexivity of equivalence, right? Any formula is equivalent to itself. It's the first theorem that we proved. So that means A or bottom is equivalent to A or bottom. It's an absolute theorem. And our proof is complete because this is equivalent to an absolute theorem, meaning it is itself an absolute theorem. Now, talking about distributivity, our distributivity told us that you can distribute or from the left side to an equivalence. This was an axiom that this is equivalent to C or A is equivalent to C or B. Now, can I also distribute it from the right? Of course you can. You just need to apply the symmetry first, right? So even though it's not an axiom, we can first apply the distributivity, swap these two, and then so I left to prove this an exercise, but this is an equation style is the easiest way to do this. Just swap, start with this side. The next step, just swap these two. You get C is equivalent to A is equivalent to B, and then apply the axiom. So write the details as an exercise. And now this we also call distributivity of disjunction over by equivalence, because it's the same really. So now that we know it's true, we'll just call it, we'll call both the same thing, as we always do with the distributivity. Another theorem is this double distributivity. Now that I can distribute, if I call this formula D over this, then the result, if D is itself A is equivalent to B, then that would be equivalent to A or C is equivalent to A or D is equivalent to B or C is equivalent to C or D. So this, again, the proof is completely obvious when you think about it. What you want to do is first call this formula a D and apply the distributivity. So let's start with this side. Now, think of this as a formula D. Apply the distributivity. It's equivalent to D or C is equivalent to D or, sorry, D already exists. D is about, sorry, call it E. Sorry, I forgot that D exists. Call it E. So E or C is equivalent to E or D. So this is E or C is equivalent to E or D. Now I want to distribute C from this side over this. So I'm going to take this part, and I know it's equivalent to A or C is equivalent to B or C. It's called the distributivity. But in order to do that, I need Leibniz, because this is a subformula of this entire formula. That means apply Leibniz when this is called P. Now the C part of the Leibniz is going to be P is equivalent to A or B or D. And apply the distributivity. You can just write distributivity of disjunction over by implication. And this is what you get. You get this side replaced with A or C is equivalent to B or C. Now do the same thing here, distribute D over this. But again, then again, this is just a subformula. So let's call this P. We're applying Leibniz to our axiom of distributivity of disjunction over by implication. I call this P, and I'm allowed to replace P with what is equivalent to this formula, which is exactly A or D is equivalent to B or D. If I took the C part of the Leibniz to be this is equivalent to P. Right, this Leibniz thing is quite easy, right? You just have to remember, I know, again, this is a little bit long to write things, But it's not that bad, right? You just write what you want to apply. You just write like 4 letters here, an axiom that you're applying or absolute theorem that you're applying. And the part that you want to replace it called P. Keep the rest and call that your C part P fresh. Fresh here means it doesn't occur in A, B, C, or D. Another theorem. A or yes.
So in the final exam, and like the current exam, we get all the axioms.
Yes. So yeah, in the midterm or final exam, I'll give you the list of axioms, rules of inference, and every theorem that we have proved in the class. All these absolute theorem, like this would be included in your formula sheet. So you don't have to memorize what we have proved, but it's a good idea to remember what we have proved, so that you don't have to every time. You know your toolbox, what you're allowed to use, but they'll be given to you. Yes.
So for the assignment, because it's also
Yes, you're allowed to. Yeah, I forgot exactly what kind of. I hope I didn't give any of you in your any of these things in your assignment, but I don't think I have. So yes, you're allowed to use any of these formulas that we prove in the class for your first assignment. How do we prove A or bottom is equivalent to A? A or bottom is equivalent to A. Let me think about. Okay, yeah. So the strategy is to replace this with A or A, and we know A is equivalent to A or A. Now on this side, I'm going to have A or bottom, and on this side, I'm going to have A is equivalent to A or A. Now I can undistribute this, and I get A is equivalent. No, sorry, A or bottom is equivalent to A, and then this is going to be negation of A. So I get A or negation of A, which is an axiom. That's the strategy. It makes sense. So let's write this down. So I want to start with the whole thing. Again, this may not be the only way to prove this. I'm sure it's not, but it's the simplest thing that comes to my mind. This is equivalent to A or bottom is equivalent to A or A. What did I do here? I replaced this A with a formula that is equivalent to it. I know A is equivalent to A or A, but since it's just a part of the formula, there's this part attached to it, we're going to have to use Leibniz, call this P, right? Leibniz to the axiom A or A is equivalent to A. It's an axiom. You don't have to write every time it's an axiom, just write it down. What is the C part of the Leibniz? Is A or bottom is equivalent to P. P is fresh. Now undistribute. This is A or bottom or A. Oops, equivalent to A. This is the distributivity. of disjunction over by implication or equivalence. Now I know this is equivalent to negation of A. It's an axiom. So I'm going to call this P and apply Leibniz to what? To the, I know negation of A is equivalent to, bottom is equivalent to A. This is the theorem that we proved in the beginning of today's lecture, and we said this is, we call also the axiom of introduction of negation. What is the C part of the Leibniz? Well, A or P. P is fresh. Now, why are we done? Because this is an axiom of the idempotency of disjunction.
Professor,
Yes?
why we need to add the first step? Because the first, the equation we have and the third step is almost the same. We just added the bracket. So why we added A or A on the first step?
How else would I prove this? I mean, okay, do you have any other ideas how to prove this?
So we just added a bracket on the first step, right?
We didn't add a bracket. Now, the first step was to replace this. I know A is equivalent to A or A. So I could replace A with A or A. So I get this. It's not about brackets. We added the entire or A here, right? I mean, does it make sense?
So I didn't understand the difference from the first
I mean,
one
you're
to the
saying
third
we
one.
added brackets. Do you see any brackets here? I don't see any brackets
No,
here.
on the third,
On the
on-
third line. But this, the brackets are here anyways. This is the distributivity. Distributivity. If I don't write the brackets, it's actually wrong. Here, if you didn't write the brackets, by the way, you got a wrong formula. Because this would mean because the disjunction has priority over by implication, then if you didn't write the brackets, I read this as A or bottom is equivalent to A, which is wrong. A or bottom is not equivalent to A. It's certainly not equivalent to the previous step. So this is just a distributivity. A or B is equivalent to C is equivalent to A or B is equivalent to B or C. Sorry, A or C.
Okay.
Yep. So be careful with the brackets, by the way. Yeah, don't if you just forget about brackets, first of all, you're gonna make the mistake in the next step. And secondly, I would already deduct some point here if there were no brackets here. Yes. They are the same. I mean, they're not, they're equivalent. Already just first formula, the first and third step, we proved that they are equivalent. Oh, sorry. So, okay. I see your point now. I see your point. Sorry. In this case, yes. they are equivalent, but they're not the same. It's not clear because what we have proved here is that this formula is equivalent to this formula. We proved this, right? Step 1, 2, 3, they show us that they are equivalent, but we didn't have this. This is the formula that says A or bottom is equivalent to A. So the entire A or bottom is equivalent to A. And here, this is another formula, which is different, right? It's syntactically completely different from the other formula. There's a formula that says A or bottom is equivalent to A. But these two steps, or these three steps, shows us that these are equivalent. But in general, I mean, I didn't know this, right? It actually took me a second to realize that what you meant, and I think what the other student meant, right? But in general, you should be careful where you place in your brackets.
Professor, one more question. So
Yeah.
we used Leibniz to substitute A with A or A, right? So how do we use that step to get the third one? Because I don't see how we use the second step to get the third one.
Well, A or bottom is equivalent to A. We have distributivity, right? This is equivalent to A or bottom. Is equivalent to A or A. It's an axiom. Now, I had this, and I know it's equivalent to this. So I just wrote my axiom. All right. It's an instance of axiom of, I mean, if you write, if you don't understand it, then just read the annotation. I use the axiom of distributivity of disjunction over equivalence. Yes.
So,
If A is a tautology, then what? A is a tautology? No, this is for any formula A. Yeah. Anytime when I don't say what A is, it's just a template, like it's a schemata, right? So A is for any A. All of the theorems that we prove that combine, that consists of A, B, C, D, and so on, those are for any A, any B, any C, any D. All right, let's move on to our next theorem, the last one for today. I hope I'll have time to finish it, but let's prove a very important theorem, very useful, that A implies B is equivalent to negation of A or B. Again, a tautology that you've probably seen before. How do we prove this? Let's start with this. A implies B. I have only one axiom that concerns the implication, and that's called the axiom of introduction of implication. And so far we haven't proved anything, so this is our only hope to be able to achieve something. And I know that by that axiom, this is equivalent to A or B is equivalent to B. Now what do I want here? All right, how about we use the thing that we just proved, that A is equivalent to A or bottom, but just use it for B. So here, before I write it, I'll just make up my strategy. If I replace this with bottom is equivalent, sorry, bottom or B, then I can undistribute this, and this would be equivalent to A, or bottom is equivalent, sorry, A, sorry, A is equivalent to bottom or B, and then this is negation of A. Yes, it works. So let's write this down. So what did I want to do? I want to be able to replace this with B or bottom, and I know B or bottom is equivalent to B, even though I might need to use an symmetry there, but I'm going to skip that symmetry. So use Leibniz. I know B is equivalent to bottom or B. We proved B or bottom, but bottom or B, just a symmetry applied to it. So I'm going to use it. What is the C part of the Leibniz? This is the part that I wanted to change, so let's call it P. The C part is A or B is equivalent to P. P fresh. What do I get? I get A or B is equivalent to B bottom or B. Now undistribute this, that means use the distributivity. Of disjunction over equivalence. Again, it's the axiom that we have, and this tells me this is A is equivalent to bottom or B, and now I know that A is equivalent to bottom is same as negation of A. I just need to use Leibniz by calling this P. Leibniz negation, or A is equivalent to bottom is equivalent to negation of A. The C part is P or B. P is fresh, and we're done. Any questions? Right? We proved that A implies B is equivalent to negation of A or B. Questions? All right. If you don't have any questions, then you all have a nice day. See you on Wednesday.
Can I ask a quick question?
Sure.
Can you tell me a good book to like study basics of logic mathematics?